On stage, welcome, Martijn Verburg.
Hey everyone. So, who was here in my talk yesterday? Excellent, cool. So I'd just like to start the show by saying Matthias Carlson is awesome. Today's going to be a little bit of a different talk than yesterday. I'm going to talk to you about a very real danger that's coming to Java developers. We, for a very long time, have had a free ride from the hardware that the guys from Intel, AMD, ARM, etc. have given us. And subsequently, we've written really crappy, poorly performing software, which has managed to take all of this beautiful hardware and slow it right down. So this guy is going to come for you, and he's pissed off. Who is the Terminator, really? Well, he's this guy. Does anyone recognize what this is? A few people? Any hardware geeks in the room? Yeah, a couple of people here. So this is good old Intel. I think it's an i5 or an i7 maybe. And you can see here, we have got multiple cores. And this is what is going to cause you developers many, many problems, because you're going to have to start thinking in parallel. Your algorithms will start having to work in parallel. Everything you do will have to be parallel. And the problem is that humans absolutely suck at thinking in parallel. So we've got a real problem here. Does anyone know what this guy is? You know, anyone from back in the 1970s or so? No? So this is one of the very first Intel chips that came out. And it was an amazing piece of hardware. I think, there we go, 1971, I think. This is the old 4004 chip. My chief scientist, Kirk, has one of these sitting at home in a nice glass case, which he likes to take out and show the grandchildren and things. Wonderful. So it was a relic of a simpler era. It didn't have multi-cores, it didn't have 5 million different caches on it. It really was, by today's standards, a very simplistic chip design. The sort of thing that a small team of engineers could actually reason about, think about, and build themselves. There is no way today that a single person or a small team could build one of these new monstrosities from Intel. So, one of these lovely old Intel 4004s. Ooh, look what we have here. We had 2,300 transistors. Cool. That's a lot. What more do you need? We had a 4-bit bus. Has anyone here coded in 16-bit programming languages? Yeah? How about 8-bit? 4-bit? Anyone? Well, there's someone up there, 2-bit? No, 4-bit's as low as we go. Excellent. I'll like to talk to the 4-bit person afterwards, because I've personally never had to do that, so that's quite good. 9-page document could tell you exactly what this chip did. Brilliant. Oh dear, we've now moved on to something a little bit more complicated. So we now have an incredible amount of speed, 3.3 gigahertz, 774 million transistors. Let's go back to the old one again. 2,300. And you know what? We're still writing slow software. What the hell is going on? Really terrible. All this sort of stuff, and here we go. This is one of the fun ones. You've got model-specific registers here where you can get information out of the CPU while it's running, so things like how your L3 cache is behaving, what your L2 cache is up to, these sorts of things. And my engineering team back at JClarity built a small fun tool called JMSR to get this information out and do some bit shifting and make nice pretty graphs out of it, etc., etc. They had to go through 7,000 pages of documentation for this one feature of the chipset alone. So that's not all of the Intel documentation on an i7, that's just one document. So if you thought you had a bad day job, then talk to my engineers, or even worse, talk to the poor technical writers who had to produce that 7,000 page doc. And the thing is, that document is actually surprisingly accurate. We found very few mistakes in it, so my hat's off to the Intel documentation writers. It's really good stuff. So, we have lots of challenges today going forwards with these multi-core machines. And there's other challenges that we face today as Java developers and as JVM engineers because the world around us is changing. It's not just the challenge of multi-core, it's a challenge of things like virtualization, and it's a challenge of having to build things for incredibly small embedded devices, all the way up to the servers that have thousands of cores on them. And Java was a language, and the JVM was designed back in the mid-90s in a much simpler era. And it has a lot of catching up to do. So this talk might hurt a little bit. There's going to be a little bit of computer science theory. Who here loved going to university and learning about computer science theory, the mathematics? Yes, good. I didn't. Personally, I actually kind of struggle with this stuff, which is why I try and force myself to go back and relearn some of this stuff every year. And it also helps so my engineers don't laugh at me. So, back to some basics. We're going to go through and cover some of the very basic laws. Do people remember Moore's law, Little's law, Amdahl's law? Computer science 101, right? We all remember back to those days? Or were we too busy playing NetHack? Yeah. So Moore's law. Mark Reinhold covered this yesterday. It's not about clock speed, it's about the number of transistors, and it's still holding true today. The guy was a genius. However, these transistors are not all being piled on a single core anymore. They're being spread out amongst multiple cores. And I think Mark alluded to it yesterday. He stated that basically the problem is just one of fundamental physics. You can't pile on more transistors without the thing melting down due to heat. There's just no more space anymore. So the engineers were almost forced to go multi-core. They had no choice, because the aliens hadn't yet landed and given us better technology. The next law we want to talk about is Little's law. Ooh, scary Greek symbols. What it basically means, there's lots of different ways you can look at it. Throughput is 1 over service time. Or alternatively, if you're Matthias Carlson, awesome guy, and you're worried about the number of people piling into the exhibition center and eating all the food and causing a big jam. You need to use Little's law to calculate how full that room is going to be on average. So as an example, we have 1,000 attendees arriving in the room every hour. Okay? So 1,000 attendees arriving in that room next door every hour. They stick around for about half an hour on average, eating their lunch, drinking their coffee, writing some code, hopefully, chatting with the community people from Oracle, maybe. So you have an average of 500 people in that room at one time. And these are the sorts of calculations that Matthias can use and the health and safety people can use to make sure we don't have a stampede. That's nice and simple to think about. What happens when 2,000 people arrive per hour? Oh dear, we are going to start having some problems. Matthias knows that the place can only sustain an average of 500. So if that rises to 2,000, he's going to have to enforce people not to stay for half an hour. He's going to have to get tough. He's going to have to get mean. He has to hire security people to say, you can only stay in the room for a quarter of an hour. And that way, 2,000 times 0.25, we still get our 500 on average, nice and safe. And it's this idea of queuing theory that is still relevant, very relevant to us today as software developers. Because we have instructions and data hitting up against points inside our CPUs, and we have software that we write which is very serial in nature. And that serial nature becomes a bottleneck. There's only so many people that you can serve at one time when you only have one service person behind the bar, and a very long queue starts forming. And if that arrival rate starts rising, then the queue starts going out of the building. Bad times. Next law, Amdahl's law. Again, don't panic too much about memorizing the formula, but what it basically talks about is how much of my algorithm can I make parallel, And if I do make it parallel, how much of it will speed up? So have a nice diagram here where, for example, if we're able to parallelize 95% of our algorithm and we throw 65,000 cores at it, has anyone seen in a Zool system piece of hardware? Really cool servers, 65,000 cores for the win. We get a speed up of about 20 times multiplier for our algorithm. Okay? The less of the algorithm that we can make parallel, so if we have serial code that cannot be split up, then the benefits taper out. We can't get any more speed up. We throw more cores at it, it doesn't make a difference anymore. So we've had a number of clients go out and buy really powerful servers. The investment banks in particular love doing this. I bought a 64-core server and my application is still slow. It didn't speed up by 64 times. They have a single-threaded application. Not going to make a difference, is it? So 3 fundamental laws. Moore's law, number of transistors is still doubling, but due to the fundamental laws of physics, we've had to split it out amongst multiple cores. This in turn has forced us to think more parallel, and we have to worry about queuing theory. We have to worry about the amount of people queuing up and only being served by one person behind the bar. And we have Amdahl's law, which is trying to teach us that if we can use things like fork and join that came into Java 7, or if we can use the new collections libraries coming into Java 8, we can automatically parallelize our algorithms and take advantage of this new hardware that's coming out. And that way we don't have an expensive doorstop sitting in our server room. So, it's all about the hardware. With software, we have this kind of problem. With today's software, and there's over 1,000 programming languages at least which you can use, which are Turing complete, you can do almost anything. Okay? You can build Facebook, you can build Twitter, you can send a space shuttle into space, you can write a little tic-tac-toe game for yourself. However, it all runs on physical stuff. And people forget that there is only a limited capacity that each of these finite things has. So your CPU only has so many transistors. Its cache is only so big. You only have so much RAM, and it doesn't matter how many virtualization tricks that you play and how many fancy VMware products that you buy. It's not going to make a difference to the piece of hardware underneath. It doesn't know and it doesn't care and it doesn't like you. Hard disk, similar problem. Especially for those of you who don't have SSD drives, if you're still on the old spinning rust drives, as I like to call them, or spinning ceramic drives, you do realize there's literally a little mechanical head which has to run back and forth and up and down and round in circles to read data. There's a physical limitation there. It just cannot go any faster. So as much as you might want to write a multi-threaded file reader, for example, it's not splitting that little mechanical head into 10 little mechanical heads. There's still a bottleneck there. You just have to remember this. Same goes with network, same goes with the bus that chats between your CPU and your RAM and your hard disk. All these limitations. So a good friend of mine and colleague back in London, a guy called Martin Thompson, has coined the phrase mechanical sympathy. And he's been trying to teach Java developers in particular for the past 2 or 3 years that we have to start thinking about mechanical sympathy again. We have to make the hardware and the software work together. We can't just blindly throw code at the JVM anymore and expect magic to happen and automatic speed-ups to happen. That multi-core revolution, as it were, has changed that forever. We're just not going to get these speed benefits without thinking about it. So check out his blog, Mechanical Sympathy. Lots of really, really interesting stuff there. So what can you do? The Terminator is coming after you. Lots of cores are coming after you. And you're going to have to learn all this icky parallel programming stuff which you haven't had to really worry about for the last 10, 15 years. So 4 things you can do. Number 1, learn the laws. If we go back to yesterday's talk, if you have the laws put up next to your monitor, you look uber smart. Your boss will think you're a rocket scientist and probably give you a pay rise. Great stuff. Actually try coding some of these laws. just write little Java programs which actually take you through Little's law and Amdahl's law in particular. There's a whole bunch of libraries you can use today to do that. You have especially the structures in Java util concurrent. Have a look at some of the queues and concurrent queues and other data structures in there. And within about 10-15 lines of code, you can run a nice little simulator showing these laws in action. Amdahl's law basically says if you don't have any serialization, if everything is parallel, you can continue to scale out really nicely. And you don't have to worry about the queuing theory, you don't have to worry about Little's theory as much. You don't have to worry about calculating how many bits of data is going to sit in a queue for an average length of time, for example. And go back and start reading your hardware manuals. Who here has the hardware manuals for the machines that they run today, their laptops and things? How many of you have actually read the hardware manual, even looked at it? We don't do this anymore. As an industry, software developers, we don't look at the hardware anymore. But unfortunately, you're going to have to again. Because you're going to have to understand how many cores your machine has. If you have a 4-core machine, and you have a thread pool with 16 threads in it, 16 does not go into 4, does it? So you need to really pay attention. You need to balance out what the hardware is capable of doing and what you're trying to make your software do. So quite often we see the case that, oh, I have a threading problem. I must increase the size of the thread pool. Well, again, if you only have 4 cores, increasing that thread pool to 100 just makes the problem worse. We have to think this through. So, I don't think I see too many people leaving the room. The next section we're going to go into some lambda calculus and some assembly code and some machine code. Just kidding. If you want that sort of thing, find Charlie Nutter in his Invoke Dynamic talks and be prepared to cry a lot. I usually walk out of his talks about halfway because I just can't cope anymore. So I'm going to talk a little bit now about what we call hardware threads. So hardware threads to us are basically the number of cores plus allowing for some hyper-threading, which is what, in particular, modern Intel CPUs do. So my Mac here, for example, has 2 physical cores, but it's hyper-threaded, cool marketing term, which means effectively it has 4 cores that I can consider as being 4 cores in terms of its hardware. I'm not going to go into the detail of the Intel engineering behind that because, quite frankly, I would need a PhD in rocket science to understand it, but there you have it. So we talk about threads. Threads were a great way to help us reason about a sequential piece of code. We want to do step A, we want to do step B, we want to do step C, etc., etc. We all want to do it on the same stack. We need something to help us control that, so we have a nice thread. Seems simple enough. In the beginning, before threads, we had this cool fork operation. And fork was really amazing because it just made basically a copy or a clone of whatever was going on. And this was nice and safe because we had no shared data. We could do stuff with caching as much as we liked. We didn't have to worry about race conditions. And for the love of God, I don't know why we ever left fork behind and moved on to these fancy threading things. Terrible stuff. I'm now going to go back before I talk a little bit more about threads. I'm going to talk a little bit again about the architecture of CPU. We stole this idea of another colleague of mine, Trisha G, who loves doing hand-drawn diagrams of complicated bits of machinery. So we have our physical cores here, core 0, 1, 2, and 3. We have the level 1 caches next to the cores. So these are the caches that you have which hold the data that the CPU needs to use most often. So you might have a number which you're repeatedly multiplying in a hot for loop, for example. That piece of data will probably end up getting stored in L1 at some point because it needs access to it. The CPU needs access to it constantly. You have L2 caches and you have these L3 caches which are shared across the physical cores. Note, however, there's no L3 cache across the 2 physical CPU chips. So these grey boxes, consider those as the little physical chips you actually put inside your computer. We all still build our own hardware, right? Yay, cool, a few people in the room. And then you have main memory, so this is just your RAM. Now there's a little interesting thing about this, and the Google Caliper guys, I think, have got a really lovely diagram on their site about this, but if I want to go get a cup of coffee and I decide I want to travel to the L1 cache to go get my cup of coffee, I'll pretty much walk over to that table and get my cup of coffee. To go to the L2 cache to do the equivalent thing, I have to walk all the way across to the other side of the conference center to get my cup of coffee. Going to the L3 cache, I have to leave Stockholm and walk all the way across Sweden to get my cup of coffee. Orders of magnitudes of difference here. How far do you think I have to walk if I have to go out to main memory? Any guesses? Pretty much the moon, that's right. That's a long way to go to get a cup of coffee. So if your programs, if your software, if the JVM is laying out its data and laying out its algorithms in such a way that the CPU is constantly having to go out to main memory, or heaven forbid, the hard disk, which is where you leave the solar system, and if you're using a spinning Rust drive, you're not even in the local solar segment, you're actually just about heading out of the Milky Way. Your machine is just going to churn and die, and your applications are going to perform very, very poorly. So we don't want to go get our cups of coffee from the moon, as little as possible anyway, and we definitely don't want to get them from out of our solar system, which is why when people naively say, "Ooh, I don't have enough RAM, I'm just going to enable the operating system caching," which is basically use my hard disk as a piece of RAM, things tend to slow down an awful lot. So if your managers are forcing you to write Java in Eclipse on only 2 gigs of RAM on a Windows machine, just give up and find another job, seriously. Not good. We also have these little things, cache lines. This is how information is stored inside these small L1 caches in particular. Typically on modern hardware, they're about 64 bytes in size, stacked up nicely there, so line 1, line 2, line 3, line 4, and they're kind of indexed, as it were, by these sets. So there's lots of different ways that the CPU can get very quickly to the data. Think of it almost like a Rubik's Cube full of little bits of data. That's one way of looking at it. We're going to get back to that point, by the way, these little cache lines. So we have this new threads business, and we had this running on a single core machine for a very long time. So my Commodore 64, the ZX80, the early Intels, early Apples, RISCs, all that stuff, all single core machines. So you had to start thinking about guaranteeing order. And in Java, we started to use volatile, synchronized, and these other concepts. And the Java memory model inside the JVM helped us do the ordering, and then the operating system goes away and guarantees it for you. Unfortunately, this means that the Java memory model and the operating system had to start doing a lot more work. So you have this concept of context switching and thread scheduling. And again, you've only got one core, only one physical thing that can run a thread at a time. So as soon as you start involving thread number 2, what you're really doing is you're sharing. And like 2 3-year-old children trying to share a piece of cake doesn't generally work too well. Usually one of them has the cake, and then the other one hits the first child and takes the cake back off it. And this all takes time, and there's a lot of crying involved. And this is why I'm still not a parent. So if you have more threads than you have physical cores, you're going to have thread scheduling problems. Painful. And for those of you who follow the Linux kernel mailing list in particular, you'll see the endless debates they have about Linux's thread scheduling system. Okay? It is the biggest bottleneck that they face today, pretty much. So cool, we now have more hardware threads. Awesome, yay. Instead of only having one cake for the 2 children to fight over, we can give them a piece of cake each. Awesome, this is good. However, the problem is we now have shared data. So we still have this concept of a single cake, and now 2 people want that exact same bit of cake. Uh-oh, this is a problem. We get nasty things like concurrent modification exceptions. We have values disappearing and changing from under our feet. And we can't see what these other threads are doing. So this is not very good. The hardware guys have started to put in extra support. So we've got compare and swap operations. We have non-uniform memory access and a whole heap of other tricks that you can go read about in Intel manuals or in Wikipedia if that's faster. So what can we do? We now have this problem where we have all of this data which is being shared by multiple threads. We need to make sure we protect that valuable data. So Gil from Azul Systems said quite a while ago that we protect code. So we use things like concurrent hash maps, we use synchronize, we use volatile, we use all of these concepts to protect our code in the hope that we protect our data so it doesn't become corrupted, so we don't lose it. There's a bunch of different techniques we can use. We've good old synchronize, we have volatile, we can use the atomics in Java util concurrent. Are people here using Java util concurrent, by the way? Who here is still only using the synchronized keyword to do their concurrency? Few people? Don't be shy, it's not that uncommon. It's all good. I'll go into that a little bit later. We have more locks, explicit locks in Java util concurrent. We have all these wonderful new structures. But we have a problem. They all have a slight performance impact, only small. Only small. So I'm going to quickly whip through some source code. Don't panic if you can't read all the source code, because I know how difficult that is to do when you're sitting in an audience and someone's got 5 million lines of source code throwing at you. There's a point to this all at the very end. So, we can run without any safety whatsoever. Lots of threads. We're not worrying about protecting our code or protecting our data. Counting, increasing the counter, decreasing the counter, and we can have multiple threads coming in and doing this, right? What the value of counter is at the end? Who knows? So it's very fast, just not very accurate. So if you're looking for a wrong answer, we can get you there very, very quickly. Cool. We can start using volatile in there. Okay, volatile will make sure that we flush the data back out so that other threads can see the most updated state of that data. And I'm going to go, at the very end, I'm going to go back to the nice little diagram of the caches to sort of explain that through. So don't panic if you don't have an in-depth understanding of what volatile does yet. So that's cool, we can do that. We can use synchronized, which we've all done for many years. Cool. We can use Java 5 explicit locks because they're a little bit easier for a developer to understand, because like transactions and transactional program, you're saying begin transaction, do some stuff in transaction. With the synchronized keyword and its ability to use implicit locks, some developers just struggle with that concept. They don't really understand when the lock on the data is started and when it ends. So using explicit locks sometimes, especially for junior developers, can be a much easier way of dealing with things. And they have some other nice properties as well. Cool. We could use an atomic integer, which internally uses the compare and swap operation on supported hardware. Again, reduces the amount of threading that's required. Cool. So lots of ways to skin the cat, lots of options. Performance problems. So this is a point that I wanted to get to. When we run it naked, really super fast. And look how slow it is as soon as we start protecting that data, as soon as we start getting the thread scheduler involved, as soon as we start getting locks involved in the Java memory model. It gets really, really slow. And this is why in the literature today, you've seen people move from the state of, oh, cool, we've got multi-core, we now need more concurrency utilities and abilities in our language to deal with this shared state. So we build new language features, we build new libraries, all of which use locking mechanisms to lock the data off nice and safely. And there's now quite a lot of research going into non-locking algorithms, non-locking ways of dealing with parallelism and concurrency, because these locks are just starting to absolutely kill the benefit of having these multiple cores. Youch. So locking kills performance. So if you're really working in a space such as low latency trading, for example, you actually don't end up wanting to use things like Java util concurrence locking strategies. You need to use much more difficult, much more advanced non-locking strategies. So I'm going to go back a little bit quickly. Back to this guy. So I was talking about the volatile keyword before, and to give you sort of an engineer's level understanding of it, as we like to call it, if you have a piece of data that's sitting nicely in this L1 cache, and a single thread is utilizing that and making it be used, that's all cool. And then a thread over on this guy here wants that same piece of data. Okay? So volatile helps ensure that the data here, so integer x, which is, say, equal to 10, is flushed out of L1, out of L2, out of L3, all the way back out into main memory, hops across, and down it goes. So I've gone and walked all the way to the edge of the solar system, and then back all the way down to the other edge of the solar system to go get my cup of coffee. One of the reasons why there is such performance impact. Cool. So talked a little bit about threading and the problems we have there. So we have lots of threads. We need to protect our shared data. You can use a variety of locking mechanisms to do this, but it does hurt your performance. So there's really interesting areas of research going on into these non-locking algorithms, and you can go to places like Martin Thompson's blog, Mechanical Sympathy, to read up more on those. Next challenge, virtualization. Everybody's going mad for this. All of the cloud vendors are all supplying you virtualized environments. Data centers are becoming virtualized. Oh, you can just spin up another instance and it'll all be fine. And magically new hardware gets created underneath, right? Nope. Why do we do it? I don't know. Is it marketing hype? Someone trying to sell more software? Don't know. Well, some people suggest that we want to utilize our hardware better. It's been well known for some time that for a lot of cases, CPUs stay silent. CPUs actually end up doing very little work. They're idle most of the time. And that's an expensive piece of hardware to waste. So if you could virtualize that CPU and have more programs, more operating systems, more things using it constantly, that's a better utilization of that expensive resource. That's one way to look at it. We like to say, or we like to think that instead of actually just saying, oh, the CPU is underutilized, we should virtualize lots of operating systems on top of it to use it, how about we actually take a look at our applications, our existing operating systems, our existing Java code, and look at its performance characteristics and say, well, why are you not using the CPU? You should be using the CPU. Change the actual application, change the operating system, instead of throwing more virtualization at it. Blah, 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 blah. What it's basically saying is that the hardware doesn't see your process. Your hardware doesn't even see a thread. It doesn't know what they are and it doesn't care. So processes don't exist as far as hardware is concerned. Remember that. It's kind of analogous to a concept called flatland, where these creatures only live in a two-dimensional space. They have no idea that the third dimension exists. Or if you think of fish swimming in the ocean that live beneath the waves their whole lives, they have no idea that there is this thing above them, an atmosphere. Similar idea. So the problem with virtualization today is that people are piling and piling and piling more virtualized operating systems on top of the same hardware that they had in their data center already. And as I said before, you cannot create more hardware out of nothing. It just doesn't work. You have all of these little problems when you start virtualizing. Go through them. You now have more operating systems and more application servers and more things doing more network traffic on the single piece of hardware, on a single network card. Network starts to get overloaded. You have lots and lots of thread scheduling issues. So if you remember me talking before again about we have a few children wanting to share that piece of cake, you've now just added another 40 children to the birthday party, and you don't even know who they are. You don't even know who their parents are. They just came from nowhere. A real worry. So you might have a perfectly tuned application running on your nice little virtualized operating system, and the bully next door, and the operating system next door, virtually speaking, has got this horribly badly tuned app which is eating up all of the hardware and gives your application no chance to move. That's a bit mean, isn't it? This is what happens in things like Amazon EC2, by the way, so be careful. So what can you do? Well, when you see your CTO or your CIO come back from that flight to New York with the trade magazine saying, move to cloud, move to virtualization, you will save 100 million kroner a year. Actually sit down with him or her and work out what the real cost of ownership is going to be. What does your growth curve actually look like? Do you really need to horizontally scale so quickly that you need to have this capacity to virtualize? Because the one great thing about virtualization is that if you do it right, you can spin up new servers incredibly quickly. So if you are involved in software that does need to horizontally scale very quickly, then yes, virtualization is certainly something you should look into. But outside of that, if you're just a regular old kind of application, you pretty much know that you're going to have a slow but steady growth curve, then virtualization, I would suggest, is maybe not for you. Running on bare metal is actually okay. There's some tricks you can do with the hypervisors and the virtualization software. So I mentioned before how that the bullying child next door can use up all of the CPU and you don't even know them. You can actually ask the people, or you can look at the configuration of the software of the virtualization layer and say, I want to pin my virtual operating system to at least one core, or to at least 2 physical cores. And that way you are guaranteed to at least have some of that hardware. You do the same thing with RAM as well. But these are all little tricks that you're having to play because of all of these other bullies in your neighborhood. There are many reasons to move to the cloud and to move to virtualization. Performance is not necessarily one of them. People mistake performance for scalability. They are two very, very different things. Next challenge, the JVM itself. We have good old write once, debug everywhere. People are familiar with that phrase from the old Sun marketing days. We have some issues around garbage collection and its ability to scale with new modern hardware. We have these really cool GPUs, which have got thousands of cores typically, lots of processing power, and we can't use them. Not so good. So Brian Gertz and the people at Oracle and Red Hat and IBM, who are all working on Hotspot in the JVM, they've got an awful lot of work to do. So we have this write once, run anywhere principle. But the problem is that the hardware is constantly changing under our hoods. Android devices have come out with 750 different screen configurations. We have new types of file systems coming out on the Linux kernel every year. And we have different power needs. We have small embedded devices, which have almost got no power at all to drive them, all the way up to giant server farms, which have enough power to run in a small city. We have the cost of our strong memory model in the JVM. It's very, very conservative because it's very safe about your data. So again, you have these locks inside Java, inside the JVM, which enforce that the data is correct and doesn't get corrupted. But it does slow things down because it effectively serializes everything. We have this visibility mismatch. So again, I showed you before with the pictures about the data sitting on the L1 core and the cache lines. That's how hardware thinks about how data is stored, as it were. But the JVM doesn't think of data in that way. It has it in, Java, C++ data structures locked behind threads. Very different. Talked a little bit about volatile and how volatile forces that data to move from one core where it's nice and close to its CPU all the way through main memory back out to another core that wants to use that piece of data. And the worst thing is that If you remember, the cache lines are about 64 bytes in size. That means you can fit quite a few integers in there. So you might have declared one of your fields in your Java class as volatile, and its friend is sitting along next to it. So guess what happens when that cache line is evicted and told to go fly around the solar system and back around? Yep, you've taken your neighbor for a ride as well. Not cool. GC scalability is an issue. So in short, garbage collection is actually not about the dead things. Modern garbage collection algorithms, including all of the ones included in the hotspot, actually the cost involved is with the live objects. GC basically involves tracking through, finding out what's alive and making sure not to remove that, not to delete that memory. So if you have more RAM, if you have JVMs with bigger heaps, there are now more live objects for the GC subsystem to track. And this just slows GC right down. So you have these problems where you have 20 gig heaps, and GC pauses can take up to half a minute, maybe even longer. We've seen pauses of 10 minutes before, because the GC subsystem is taking so long to track the live objects all the way through memory. Big problems. So the new G1 collector is partly come in to solve this problem on hotspot, and there are some other alternatives as well out there. So I'd highly recommend that if you are starting to move into these larger heaps, that you take a look at the G1 collector. It's now fully supported under Java 7. We can't use our GPUs today, so we have these incredible powerful bits of hardware which we can't actually use Java on. That's really sad. We have thousands of cores we could use, especially to run things like Monte Carlo simulations, really compute-intensive type of things. So luckily there is a new project on the way, Project Sumatra. If you're interested in running Java on GPUs, then I highly recommend that you jump into that project and help out. So some practical things you can do. If you're not using Java util concurrent, as I mentioned before, please do. Avoid locks where you can, if you want performant, multi-threaded applications. You can use unsafe to implement lock-free concurrency. But this is a little bit dangerous. Cliff Click has a library which does use this, and him and Doug Lee and about a handful of other people in the world are probably the only ones qualified to do this. Unsafe means unsafe. There is a reason why it is called that class. So unless you have a PhD in concurrency and understand the Java memory model, please do not play with this yourself. You will just end up shooting yourself in the foot. You can work around GC problems. You can start allocating memory off the Java heap and into native memory. And people like the Cassandra project do this. A whole heap of other caching type products are starting to do this. So basically, your data is just being stored in native memory as opposed to inside the JVM, in short. Peter Lowry has a thread affinity project where you've got this concept of making sure that data on one thread stays on one core. And if you want to help out and make sure that the future of Java is going to be okay in this world, then join Adopt OpenJDK. Last but not least, the challenge for Java itself as a language in this modern world. Thread is a very low-level construct. I think Mark Reinhold called it the assembly language of concurrency programming. Has some really dangerous operations in there which are not safe to use. At the very, very least, you use Java util concurrent. If you can, use a language on the JVM which is more inherently thread safe. Look at Closure. Look at what Scala is doing with actors and its ACCA framework. We have functional and parallel programming now blending in together. So a few of you have probably attended sessions on lambdas today and yesterday, yeah? I think these things are really, really cool, and kudos to Brian Gertz and Doug Lee and co for getting these into Java. They are going to completely save our asses from the Terminator, which is really cool. If you need to use the equivalent of lambdas today, there are plenty of other languages, again, on the JVM, which will help solve these sorts of problems. You can look at Groovy, you can look at Scala, JRuby, a whole heap of other languages, which will be very useful. I won't go too much more into detail about lambdas collections because there have been other excellent sessions on this already today. File systems. Who here enjoys writing file system code in Java? Horrible, horrible stuff. You can't follow symbolic links, you've got no idea what the system's doing, you can't look inside zip files, all sorts of problems with it. So Java 7, if you haven't moved to it already, you should. You can now do wonderful things like asynchronous I/O. You can actually have multiple threads reading that large 1 gigabyte file off the disk or reading that massive stream coming in off your network. Very handy stuff. Again, practical things. Read that book. It is utterly, utterly amazing. Brian Gertz has this brilliant capacity to actually take a very complicated topic, such as the Java memory model, and distill it down into the sorts of level of detail that I can understand. And if I can understand it, then all of you can absolutely understand it. Okay, I was bottom of my class in computer science, so you guys will be absolutely fine. So definitely read his book. It's got lots of practical examples in there on how to write good, concurrent, safe code. Move to Java 7. Java 6 is being end-of-lifed, so please, please, please move to Java 7, or at the very least, get the Oracle support contract for Java 6, so I get my little finder's fee as well. Thank you. So, in conclusion, if you don't want the Terminator to come and get you over the next couple of years, you need to learn about hardware again. Start reading those manuals. Know how many cores that the server you're running on has. Know how much RAM you have. Know whether you've got a spinning Rust drive or whether you've got an SSD drive. And by the way, if you don't have an SSD drive, go get one immediately. It makes the difference between traveling outside of a few solar systems and traveling across the entire galaxy. That's the order of magnitude you're talking about. So make sure you get those in there. Use virtualization with caution. Don't just blindly go out and run 10 virtualized operating systems on one piece of hardware that used to only run one operating system. You're just going to end up making everything perform horribly slowly. The JVM needs to evolve, and we need to help it. So the guys at Oracle and OpenJDK, they need your support, they need your help, they need your feedback with the new libraries coming in, with the new lambdas coming in. Download Java 8 today and start using it and start giving feedback. Please, we absolutely need this. And the last thing is start to think in parallel. Start drawing out diagrams of how you can split up your algorithms so that parallel threads can run them. Because as Andal's law showed you, as the number of cores increase, the speed up time of your algorithms can increase with it. So don't become extinct like the dodo. Be like Sarah and go out and kick the ass of that Terminator. Thank you very much. Some acknowledgements here. Thanks for listening, and if you have any questions, just come up and see me afterwards.